how we derive the input impedance at the end, another end. Okay, this is how we derive. We did this last week, and we obtained this equation. And today we are going to find the 5 spatial cases, 1, 2, 3, 4, 5, for this equation. Okay, so what happens if you connect your transmission line to a short, to open, to a match load, to if the transmission line, the wavelength of the transmission line, it is the quarter wave transmission line, or it is a half wave transmission line. Okay, 5 spatial cases. I think this is more clear, more beautiful about what I drew last class. So there are 5 cases. Okay. Spend some time to go through all the details to make sure you can understand. Then we can start. We can start to go through these 5 cases. Okay. So this is the more beautiful tangent theta. I drive that in. I use the Mathematica. I use the software. If there's a theta, your phase, if that's a theta, and at this point it is 4 pi is here, 2 pi here, and the pi here, and this is pi over 2, and 3 pi over 2 here. Okay, tangent theta. Okay, for the first case, your case A, if it is short, means your ZL is 0. So look at this equation. What happens if ZL is 0? This term is 0 and this term is 0. Z0 and Z0, they cancel out by each other and left another 0. You have only 1 0 left. So you obtain your input impedance equation become this simple form. It is Z0 multiplied Z tangent beta L. Okay? Okay? And for I erase it. There is an equation of gamma 0, or you can directly use this equation. If your ZL is 0 here and here, you cancel your Z0 in the numerator and the denominator, and you obtain your reflection coefficient at Z equal to 0 or L equals to 0, it is -1. Okay? So your reflection coefficient is -1, and you can write down the rest of your total voltage on the transmission line because of this -1. You can obtain your voltage anywhere on the transmission line. It is an imaginary number. Your voltage becomes an imaginary number because of Euler equation, exponential J beta L minus exponential minus J beta L become sine beta L. Okay? So your voltage on the transmission line, it is an imaginary number, and it is a function of sine. And the current, you do the same thing. You obtain current, it is a real number of cosine beta L. You just put everything inside, so there's no technique, nothing special. You just put everything except the important key point. You have a Z0, gamma 0 is -1. If you put gamma 0 is -1, you can obtain your voltage function and the current function. Okay? So you directly connect the transmission line at the end. You connect the signal line to the ground line at the end of transmission line. And then you can obtain the voltage and current everywhere on the transmission line according to this equation. Okay? You obtain input impedance and the voltage and the current anywhere on the transmission line. Got it. These two equations. So write down these three equations. What? That's so fun. For the short at the end, which means your voltage is the potential drop at the end is 0, right? You can see that it is short at this end. Your voltage is 0, the total voltage is 0 at Z equals to 0, right? You can see from this, the equation of current, after quarter wavelength, if your L is lambda over 4, or you say lambda G over 4, it's the same notation, okay? Your current will become 0 at lambda over 4. If your wavelength is a quarter wave transmission line, you short. You should not draw it. If this is short and the length is lambda over 4, you will find that it is open here. Interesting, huh? If this is a quarter wave transmission line, you short at the end, you will feel like it is open at the other end because the current at the other end it is 0, so this is open. Understand? So you can also look at the input impedance at anywhere of the transmission line. Because it is short at the end, so the input impedance at Z equals 0, it is 0. But after a quarter wavelength, the input impedance is infinite. As I say, it is open now. You guys understand? Short become open if it is a quarter wavelength transmission line. Short become open according to these three pictures, and according to these three functions. I know you cannot accept that. How can short become open? But think about that now. You are thinking like in the RF. Okay, this is RF transmission line. It is RF transmission line, high frequency transmission line. Your voltage your current, your impedance is changing according to your position. Okay? So you connect your transmission line to a load which is short. It will become, input impedance will become infinite at some position. It looks like open. Short become open. Okay? Okay. This is important. How about if I connect my transmission line to an open load? Open means your ZL goes to infinite, and your ZIN, your ZL is much larger than other parts. So you don't see this term and you don't see this term. Okay. Let me use marker. Because ZL is very huge. Okay? So this one is very huge comparing to ZL. So this one disappears. And the ZL is very huge comparing to Z0 disappear. ZL and the ZL can be cancelled by each other, and you left minus Z0 multiplied say cotangent beta L. This is 1 over tangent beta L. So become cotangent beta L. Okay? Okay. So let's do very similar thing. The reflection coefficient at Z equal to 0, it is 1. It is 1. Okay? And the voltage and the current function become this one and this one. And the voltage function, it is the real number of a cosine function. And the current, it is the imaginary function of a sine function. Okay? So when you connect to an open load. So let's look at the same the figures of these three functions. When you connect to open, means your current, it is 0 at the end, and then Z equals to 0. After lambda over L, you will find out that the voltage becomes 0. So at this point, it is short. Okay. So what we can observe? Open becomes short, short become open, open short, open short, open short, open short. Repeating. If your wavelength is a multiplication, an integral number, is an integer number, 1, 2, 3, 4, multiply a quarter wavelength, your input impedance will become, if it is open at the beginning, will become short and open and short and open and short and open, repeating forever. If this is a lossless transmission line. Okay. If this is a lossy transmission line, the signal will decay. But if it is a lossless transmission line, it's open short, open short, open short, open short. Okay? Then you find out that also the function of input impedance will become from open, infinite, right? Become 0, it's short. Become open, become short, open. Okay? So this is one of the interesting situation of a high frequency transmission line. That's why lambda over 4 and lambda over 2 are important. You can see that open, short, open, short. Or you can see that, okay, changing, or come back to original, come back to original. If the transmission line, it is a half-wave transmission line, you will regard that like there is no transmission line. It will be the same impedance as what happened at the beginning, okay? So when you design a circuit, you use a transmission line longer than half wavelength. That doesn't make sense because you are wasting your material, you are wasting your line, right? Because they come back to something at the beginning. We don't use a transmission line longer than lambda over 2, except you want to waste your money. Or maybe that is an attenuator. You try to decay your energy. You try to attenuate your signal. Okay, except that. But in that case, if you want to do a design, we usually want to make it as small as possible, right? Okay? That makes sense. So, okay, so the third case, actually, we jump to D, right? There's no C. This is from, I don't know why it's D match. No, there's no match. Okay. Okay. Let's think about match. If ZL equals to Z0, what is Z in here? If ZL is Z, if Z0 is ZL, this one, your numerator and the denominator, they cancel each other, right? So your input impedance is Z0 again. Okay? So nothing changed. That's why we say matched. It's a perfect situation. They don't change anything. Your ZL connect a transmission line will become pretty much the same thing. No matter how your wave line, your transmission line, how long it is, they are the same. They're matched. And the gamma is 0. There is no reflection coefficient. For the time we talk about voltage, we have a forwarding voltage and the reverse voltage, right? For the match case, there is only forwarding voltage. There is no reflection. Or you can say your S11 is perfect. It is minus, S11 is a minus infinite number. It's better than not only just 20 dB, not only 30 dB, not 40 dB, it's 100 dB or infinite dB. It's perfect. That never happened in the real world, right? Like you guys know S11, if you have number more 20 dB, 30 dB is a better design, right? If it's totally matched. Okay, for the third case, it is matched. Okay? And the D and the E, you can see the case of actually, we show E first. For this one, half wavelength is E. Your L is lambda G over 2. Then your beta L is pi. And you can read through this one. If your tangent theta is 0, your impedance tangent theta, this is 0 and this is 0, right? And your ZL and the ZL cancel out by each other. Your Z in is ZL. Okay, the same conclusion as what we just said. If your wavelength is half wavelength, your transmission line is half wavelength, is the same result as there is no transmission line. Okay, you go back to Z in equals to ZL. So you can use this equation. Z in is ZL. The input impedance here is totally the same as your input impedance at lambda over 2. So this is case E. Okay, the fifth case. And for case 4, or case D, is a quarter wave transmission line. Quarter means 1 over 4, 0.25. Okay, quarter wavelength transmission line, lambda over 4. And you got the infinite number for tangent beta. It is infinite. So if this is infinite, this is infinite. Comparing to this term, you don't see this term. Comparing to this term, you don't see this term. You got, and you cancel J, and you cancel tangent beta out. You obtain your input impedance is the square of your characteristic impedance over your load impedance. It is extremely impedance. This is very important. This equation is super important. People use the quarter wave transmission line to decide many things. You use the quarter wave transmission line as an impedance transformer, not only used for open short load, but for any other impedance. Okay? If your load is any other impedance, and you have a quarter wave transmission line, you will use this equation to obtain the new input impedance according to this equation. Z in equals to Z0 squared over ZL. Let me make an example. I have an impedance of the load. Maybe 100 ohm. Okay? But I don't like it. I want 25 ohm. How can I change 100 ohm to 25 ohm? How? Can anyone change the impedance using high frequency transmission line? Can anyone? I want to change 100 ohm to 25 ohm. Can I do that? Yeah, do you want to try? No? Can anyone? I want to change. the impedance. Why do you need to change impedance? I have a transistor. I want to design an amplifier using a transistor. The best gain. I want the best gain of the transistor. I change the impedance at the input and output point according to some reason. I change the input impedance to other impedance, then I can obtain a good amplifier. That's what students do. The same. It is a simple question. I use something to change the impedance over some frequency, then I can obtain maybe a power amplifier, a gain amplifier. This is what we do here. Okay? I change impedance. Okay? Let me just give you a quick answer, okay? So what is the answer for that? So this is actually, it's more advanced impedance changing. This is more advanced. And you guys, many of you know how to do it. And you don't know how to answer this easy question? You guys are just shy. Okay. Totally the same thing. Totally the same thing. I want to change 100 ohm to 25 ohm. I can use the equation I just mentioned. Z in equals to Z L over the square of Z0, right? Am I right? What is Z in? This is 25. I want 25. Equals to, there is a transmission line with the characteristic impedance Z0. Okay, a square. And what is ZL? 100, yes. So, your transmission line should have the characteristic impedance of 50 ohm. What I need to do is I connect this load to a transmission line which has the characteristic impedance equals to 50 ohm, and your L is quarter wavelength. It is also important. Then I will obtain 25 ohm here. Okay? I can change impedance. I can design circuit. Okay? This is very important. in your textbook, POSA also mentioned about insertion loss, but I think many of you already you saw these equations before when we are doing the wave impedance eta, right? The reflection coefficient ZL minus Z0, ZL plus Z0 or Z1, it depends on you have different material, right? If your Z is ZL or Z1 or ZL, it is a load impedance. And if your load, it is not the only end. There is another transmission line connect to your transmission line. It's like you connect two infinite long transmission line to each other. Okay? For the first transmission line, it is ZL, and the second transmission line here is Z1. You can also use this equation. Your reflection coefficient at Z equals to 0 is Z1 minus Z0 over Z1 plus Z0. Okay? This case is a little bit different between here, right? You didn't connect to just a load. You connect to another line, and this line is infinite load. So there are two characteristic impedance because there are two transmission lines. Okay? You connect two lines with each other, and your reflection coefficient here is this one. And according to something you are supposed to already understand, your insertion loss, or I would say this is a transmission, this is a reflection and the transmission. Your transmission coefficient T, it is 1 plus gamma if your energy is, there is no loss. You obey the energy conservation law. Okay? So you can directly write down 1 plus gamma here. How much you passed through the discontinuity go to another direction, plus the energy reflect back if they are the same. The summation is keeping the same. You can use the equation and obtain T equals to 2 Z1 over Z1 plus Z0. Okay? Or you can transfer to something we are familiar with, which is return loss and insertion loss. You just take a log of the absolute value of your gamma and the T and multiply, and then use the log function and multiply by 20, and this number has the unit dB, unit again guys, unit dB if you take 20 log, and you get minus sign here because you are talking about the loss. So the number of the loss is supposed to be a positive number because you already said this is loss, right? Okay, so POSA mentioned that. Okay, let's take a little break, maybe a little bit early. We take a break and we come back early, okay? So we will come back at 5:15 because I don't want to be interrupt when I'm talking about the Smith chart, which is very important. Okay, come back 5:15. Okay, take a rest.